We are analyzing a highly specific type of equation, the homogeneous linear second-order differential equation with constant coefficients. Visually, it takes this exact form, with a strict physical constraint that the leading coefficient, a, cannot be 0. To solve this, we face a mechanical tension. We need to find a curve that, when scaled, derived once for slope and derived twice for concavity, allows all three versions of itself to perfectly add up to 0. There is only one mathematical function capable of this kind of self-replicating behavior, the exponential function. Every single solution to this differential equation is either a direct exponential function or it is constructed entirely out of exponential pieces. Because of this rule, we can confidently assume the solution will always look like y equals e to the mx. By assuming this exponential shape, we force the calculus problem to map directly onto a much simpler mathematical structure known as an auxiliary equation. Plugging in that exponential guess strips away the complex derivatives. We leave calculus behind entirely, stepping into the predictable, solvable realm of pure algebra. Let's test that assumption. We set our baseline guess as y equals e to the mx, where m is a constant we need to find. The first derivative pulls down an m, the second m squared. Substituting these back, a, b, and c pair with the m terms, sharing the common e to the mx. Since exponentials never reach 0, we cancel e to the mx. The remaining terms inside the parentheses must equal 0. This specific remaining polynomial, am squared plus bm plus c equals 0, is formally defined as the auxiliary equation. The dynamic physical behavior of the entire calculus system is now locked completely inside finding the simple algebraic roots of m. Since we are dealing with a quadratic polynomial, the primary tool to find our m values is the quadratic formula. This logic tree shows how the value underneath the square root, the discriminant, b squared minus 4ac, dictates three distinct mathematical pathways for the system. Case 1 occurs when the discriminant is greater than 0, yielding two distinct real roots for m. We plug those values directly into our exponents to get two baseline solutions, y1 and y2. For a second-order equation, we require two separate solutions that are linearly independent, meaning one cannot simply be a scaled copy of the other. To prove independence, we use the Wronskian determinant. Because our two roots are different, the Wronskian is non-zero, confirming these functions form a valid independent set. For systems with distinct real roots, the general solution is the linear combination of these two different exponential curves acting together. Case 2 occurs when the discriminant equals exactly 0. This leaves us with a single, repeated real root. This leaves us with only one exponential function, yet our system requires two independent solutions. To find that missing dimension, we multiply the first exponential by x. This linear scaling preserves the exponential behavior while ensuring the two functions remain independent when the roots overlap. This second solution provides the necessary mathematical dimension to describe the system without violating the constraints of the original auxiliary equation. Finally, case 3 occurs when the discriminant is less than 0, creating complex conjugate roots. Substituting these complex roots results in an exponent containing an imaginary number. A complex exponent cannot be plotted directly on a real-world coordinate plane, creating a gap between the algebra and the physical system. We bridge this gap using Euler's formula. Euler's formula translates imaginary exponentials directly into trigonometric functions. As a point rotates on the complex plane, it maps out sine and cosine waves. By choosing our constants c1 and c2 carefully, we can force the imaginary components of the equation to cancel out. Setting the constants equal to 1 isolates the purely real cosine function. Using opposing constants, one positive and one negative, isolates the purely real sine function. Complex algebra acts as a structural bridge here. Even systems governed by imaginary roots describe real-world periodic behaviors, like mechanical oscillation. This table organizes the three realities: distinct exponential growth or decay, scaled repeated roots, and periodic sine and cosine waves. In case 1, the auxiliary polynomial factors into m equals -2 and m equals 1. Placing those roots into the exponents yields the general solution. Case 2 gives us a repeated root of m equals 1. We add the x multiplier to the second term to maintain the two-dimensional solution space. The complex case follows the same logic. Factor the roots, apply the trigonometric translation, and the solution emerges. Analyzing the initial coefficients of a linear system allows us to accurately predict if that system will grow, decay, or oscillate. The exponential function is the universal building block of all linear systems. It translates calculus relationships into predictable, solvable algebra. The complexity of the system is distilled into those three algebraic cases. Once the auxiliary equation is set, the path to the solution becomes a matter of arithmetic.